Hi, everybody. Welcome to the webinar. This is Forecasting with Predictive Analytics, and we're going to get started. My name is Caitlin Onthank. I'm the marketing statistician here at Salford Systems, and I'll be taking you all through a little tutorial on building a forecasting model with data mining techniques. So you will be getting a follow-up email today if you registered for the webinar. You'll be receiving the recording, a 30-day trial evaluation of the software that I'll be showing you, the slide deck, and a tutorial with the data set so you can replicate the analysis on your own. You can still register after the webinar is over if you'd like to receive the materials, or if you want to send them to any of your colleagues, and they can download the materials as well. So again, that follow-up email will be coming either later today or tomorrow. So a quick outline of what we'll be going over today. I'll talk about what forecasting is in general. Then we'll be looking at a specific problem. We'll call it the Brazilian oranges problem. I'll explain a little bit about the main data mining technique we'll be looking at today, TreeNet stochastic gradient boosting. We'll look at incorporating some time series components, forecasting future sales, and then we'll also compare it to standard regression so you can see the difference. After that, I'll go over some case studies just to show you a variety of different ways that you can use data mining and forecasting. If we have time at the end, we'll do a Q&A, and if I don't get to your question today, I'll be addressing all of your questions individually via the email that you registered with. Okay, so broad definition of forecasting is the process of making predictions of the future based on past and present data. And what data mining allows us to do is leverage the data out there that has some of these characteristics. So if your data has variables that change over time, as well as static data, you might have hundreds or thousands of independent variables. Your data might reflect today's ever-changing economic environment. And you might also find that your data can underperform in conventional statistical or time series modeling situations. And so data mining attempts to address all of these problems. And as with any techniques, there are benefits and risks to forecasting. Obviously, if you can build a great forecasting model, the benefits are reducing the uncertainty of the future. You can gather evidence for business decisions. For example, if you're working on a retail problem and you build a great forecasting model, you'll be able to control your inventory, you know how much to buy. And if you're revising your forecast as new data comes in, your model will only be stronger. On the other side, there are some risks to forecasting. If you have a lot of inputs into your data that change over time, such as market conditions or consumer behavior, and you see any slight fluctuations in these inputs, your entire forecast could be rendered meaningless. So keep these in mind as we talk about the forecasting models today, that while there are some benefits, it can be very risky. So the problem we're looking at today is the Brazilian oranges problem. And this is the data set that will be in the follow-up email that you'll get. So you can play around with it yourself. Since we only have a 45-minute webinar today, I will be limited in what I can show you for analysis, but I'll give you some suggestions on further analysis that you can do yourself. And that's why we'll be giving you the data set to look at on your own time. So this is in-house data from a Brazilian grocery chain. But there are also similar publicly available data sets out there. One example is the Walmart sales problem on Kaggle. And I have a link to this here too. So when you get the slide deck, feel free to go explore that data yourself. The objective of this problem is to predict the daily sales of oranges in 10 different stores in Brazil. In our data set, we have about 4,000 records of daily sales and 6 different characteristics or predictors that we'll be using. It's pretty straightforward, our key tasks here. We just want to know which variables are affecting the sales of oranges and how these variables are affecting the sales. After we've looked at those two questions, we can look at actually using our model to forecast sales of oranges in the future. So before we start using this data, I'll just give you a quick screenshot here of what the data set looks like. The column in red, sales, is what we're trying to predict. We also have variables such as date, store number, month, day of the week, unit price of oranges, date in which the store resides, climate, and whether there's a promotion on that particular day or not. So it's important to see here that the structure of the data is ordered by date and is also aggregated by store. And this will come in handy later when we're starting to look at incorporating time series components into our analysis, such as lagged variables. So I'll mention this now, and I'll also point it out later while we're looking at the data in the software. And it's important too, if you're working with your own data that might be ordered by date or aggregated by certain variables, to make note of that so you're not starting your analysis with data that's not in the right format or not ordered properly. So again, we're trying to predict sales here using these other variables. Now that we've talked about the problem, I'm going to shift into a brief overview of the data mining techniques we'll be looking at today. I can't explain them in full depth in such a short amount of time, but I'll give you a little bit of flavor of the techniques, and then we'll look at implementing them in the software. So the basis of what we're looking at today is a regression tree. Now we call this CART, which stands for Classification and Regression Trees. What this does is a simple partitioning of your data set. So I have a picture here of a CART tree on the right. And simplest way possible, I'll explain that you have all of your data in this top node of the tree, this green. And you want to separate this data into two subregions based on a certain criteria. So say you have a group of people that you're looking at and you're trying to separate them. You're trying to learn about if there are any patterns in this group of people. You might decide to separate them by age. Everybody less than 40 to one side and everybody older than 40 to the other. And this is what CART does. It keeps partitioning your data into different subregions. So in the process, it separates relevant from irrelevant predictors. The results are simple and easy to understand in the form of this tree that you see to the right. You don't need to do any variable transformations on your own, and it's also impervious to outliers and missing values. So there are several advantages here to using a regression tree. CART has become known as the fastest, most versatile predictive modeling algorithm available to analysts, and it's the foundation to modern data mining techniques such as bagging and boosting. And boosting is what we'll be looking at and actually using on our data set today. So I wanted to give you a quick overview of what a regression tree is so you can understand how it's the building block to the technique we'll be using. So this is a slide about TreeNet gradient boosting. I'll be using TreeNet on the oranges data set today. So to quickly explain how TreeNet actually works is we start with a very small tree as our initial model. So this is a CART tree, the same tree that you saw on the slide before, and also denoted as tree 1 in the picture at the bottom of this slide. So this tree 1 here has 6 terminal nodes. And this is considered a small tree. But for this first initial model in step 1, the tree could be as small as 1 split that only has 2 terminal nodes. We're intentionally building a weak model for this first step because we're going to improve on it in an ensemble of trees. The next step in this process is to compute the residuals for this first tree. So we'll run all of our data back through this tree, and we'll see what our prediction errors are. And once we have this list of prediction errors, we want to build a second tree to attempt to predict the residuals from the first tree. So essentially, this is an error-correcting sequence. We start with a weak model, and we attempt to improve upon it. We repeat that same step to grow a third tree, and so on. And usually we build about a minimum of 200 trees, but you might even find that you're building up to 5,000 or 10,000 trees in a model. So TreeNet is extremely fast and efficient, and you usually see a pretty big increase in accuracy from just using one regression tree. And I've been mentioning regression trees because that's what we'll be using to predict sales, but CART and TreeNet also work for classification. So if you're trying to classify a record into a certain group, instead of trying to predict something continuous such as sales, you could also use these techniques for classification. Okay, so let's continue on with building a TreeNet model. I'm going to switch over to the software now so we can see a live demo of building a TreeNet model on the oranges dataset. Okay, so I have SPM open on my screen right now, our Salford Predictive Modeler. This is exactly what you'll be getting a 30-day free evaluation of. You can get that directly on our website, or the instructions will be in the follow-up email. This is our GUI interface. We also have it available in the command line if that's how you prefer to do your analysis. Our classic output window here will hold all of the text results of our analysis. And if you wish, you can also create models straight from the command line here. As you can see, you can type. But we'll just be using the GUI interface today, just simple point and click to build a TreeNet model. The first thing I need to do is open up our data set. So there's a little shortcut in the top left corner of the software, a little folder, and it says open. So when I click this button, you'll see a dialog box to open a data file. So I'll find oranges.csv. I typically use CSV files, but if you'll notice, we do support many different types of file for import. We have Excel files, ASCII, JMP, Minitab, SAS, R, etc. Once I've chosen the file, I just click open, and we've imported the Brazilian oranges dataset. Once you've imported a dataset, you'll see this activity window pop up. This lets you know that you've imported your data correctly. You'll see a list of variables on the left, and you'll see information about your dataset on the right. So we have about 4,000 records, 11 variables, 3 of which are character variables. Also in the activity window, we have a dashboard at the bottom of buttons that give you different options for working with or looking at your data. We have a View Data button. This just brings up a simple spreadsheet. So I'll click that first, and we can take a second look at our data. So here we can see the same snapshot that I showed you in the slide, but now we have all 10 stores. Again, by stores, these are sorted by date. So I'll scroll down to show you here exactly what I'm talking about when I say aggregated by store. Once we switch over from store 51 to store 86, we can see that the date range starts over again. We went from December 2009 to January 2008. So if this is something you didn't notice before, it would cause some problems in your analysis. You want to make sure that you realize how your data set is aggregated. Additionally, we can see there are 2 extra variables on the end of the data set here. These are variables used for testing purposes. Because our data is time ordered, we want to make sure that we're using data in the past to build the model and then data in the future to test the model. Otherwise, it wouldn't make much sense to use future data to predict the past. So these variables are set up to have a value of 0 for the first 80% of the data and a value of 1 for the remaining 20% to test. Again, this is aggregated by store. Okay, so we've taken a look at our data. I'm going to go back to that activity window so we can look at some of the other activities. There's a shortcut at the top here to open your activity window. You also have the option to run some descriptive statistics on your variables, create frequency distributions, compute a correlation matrix, do some simple data preparation, set some options, score your data, which we'll be looking at later, and finally build a model. And so this is the one we're interested in now because we want to build our TreeNet model. So when I click the model button, we see our model setup window. This model setup window is the same in this first tab, no matter which analysis engine you're using. So in the bottom right corner, we have a drop-down menu for analysis engine. Now, all of these engines that you see here will be available for you to try out in our evaluation. But the first one we'll be looking at is TreeNet gradient boosting at the bottom. So I'll select TreeNet. I also want to come up to the upper right corner of the window and check that our target type is regression. So again, if you have a different problem where you're trying to classify records into certain groups, you'll choose this first option, classification. So now we want to tell the software which variables to use in our model. In this target column, we'll select sales, since that's what we want to predict. And in the predictor column, I'll go ahead and select all of the variables, and then we'll go through and make sure we have the ones that we actually want to use. So we do want to use climate. Month will also be a predictor, but we want to make month categorical. Right now, month takes values of 1 through 12 based on the month, and we want these to be separate categories so that we're not seeing values of 4.5 per month. Additionally, we want to use promo as a predictor. This indicates whether there's a promotion on the given day or not. And this is coded as 0 or 1. So we also want to make this variable categorical. Sales date, I'll uncheck as a predictor since this won't be useful. Date is automatically coded as categorical because it is a character variable and was appended with a $sign upon import. We won't be using store or either of the test variables as predictors, so I'll uncheck those from this column. And then finally, I want to make sure weekday is selected as categorical because this is 1 through 7 for the days of the week. So we can double check everything is selected correctly in this first tab. We want to move on to choosing a testing method. So I'll click the testing tab at the top of the model setup window. Now we always recommend that you use a testing method when running an analysis because you want to build your model on some of your data, but you also want to ensure that your model is performing well. And the only way to do that is to have a separate test sample. So typically we use the second option here, where we randomly select 80% of our data to build the model and use the remaining 20% to test the model. Because our data is time ordered, we do have to choose one of our created testing variables instead. So this last option lets us choose a variable that separates our learned sample and our test sample, and that'll be test 20t. I've also included a test 50t variable that separates the data exactly in half. So it depends on your preference if you'd like to use half the data to test as well as half to learn. In this case, since we only have about 4,000 records, I'm going to choose the 80-20 partition. So one other tab I'll look at is this TreeNet tab. This gives us controls on how the TreeNet engine runs. The first thing here is choosing the TreeNet loss function. I'll choose least squares here. It's a popular loss function to use for TreeNet regression. And I'm also going to change what we call the learn rate of TreeNet. The learn rate helps protect your model from overfitting to the learning data. Another way to think about it is it slows down the learning of your model, so you're not jumping into the wrong model too fast. So I'll change that number to 0.1. This is a typical value that I start with, and it can easily be changed if you found that you didn't get a good model. So just to recap, I chose the variables I want to use for TreeNet. I set a testing method, and I changed a few of the TreeNet control parameters. So I'll come down to the bottom right of the window here and click the Start button. So as you can see, TreeNet just grew 200 trees extremely quickly. And what our output shows us here is the number of trees built in the model plotted against the mean squared error of the TreeNet model. We're also given performance on both the learn and the test samples, as well as several different performance measures: mean absolute deviation, mean squared error, mean absolute percent deviation, and R-squared. So we'll be looking at R-squared today. Here we can see that we have an R-squared of 65% on the optimal model. Now, we haven't incorporated any time series components yet here, or the lagged variables that I mentioned before. So we're strictly just looking at using the data without denoting any lagged variables or taking store into consideration. So I'll click the summary button at the bottom of our TreeNet output window. This shows us different summary statistics of the selected model. When you open this window, you'll see many more error measures such as root mean squared error, AIC, BIC, R-squared, for both the learn and test samples. So depending on which performance measure you prefer to use, they're all listed here for you. The other important summary tab I want to look at is variable importance. So when I click this tab, we get a list of the variables included in the TreeNet model and their relative importance scores. This is a quick and easy way to see which variables are contributing to your target variable. And here we can see unit price was the most important variable in predicting sales of oranges. You might also notice that we don't see climate on this list. If I click Show Zero Importance Variables, you'll see climate appear at the bottom. So now that we've seen our first TreeNet model, I want to go back to model setup and include some lagged variables. And I'll explain what those are in a minute. We have a shortcut here for returning to our model setup window. When I reopen model setup, we still see all of our options are still selected in this first window. Our testing method is still the same. All I want to change here is clicking this lag tab. So when I click lag, we see a window that lets us choose which variables we want to lag. Now, for those of you who don't know what a lagged variable is, I'll give you a quick example. So if we want to predict the sales for today, we might decide that the sales for yesterday may be a good predictor. We also might want to use the unit price of oranges yesterday to predict the sales of oranges today. So what I'll do here is I'll put a 1 in this column for unit price, sales, and for promo. So what we're doing is we're deciding to use the value of yesterday's promotion, yesterday's sales, and yesterday's unit price to see if that will help add more information for our sales today. Now, if you'll notice at the bottom of this tab, we're told what a block variable is. Data must be sorted by any block, and lags are restarted in every block group. So we want to denote that store and month are both block variables in this data set. That's because once we move over to a different store, you want the lags to restart. Otherwise, you'll be looking at the unit price from store 51 and predicting for sales today in store 86. So we want to make sure that the software knows how our data is set up and to restart the lags in each of those groups. So again, I'll just click Start, and this will rerun the same exact TreeNet model, except including the 3 lags variables. Okay, so again, we have our TreeNet output window, and we can see we now have an R-squared value of 69%. So we were able to squeeze 4% more accuracy out of using those 3 extra lagged variables. Again, I'll click the Summary button at the bottom of the TreeNet output window. We see the same statistics here. And now in the Variable Importance tab, we see the addition of the lag variables. And these are denoted by arrow brackets with a 1 inside at the end of the variable name. And you can lag these variables as much as you want. If you'd rather look a week back, this would say unit price 7 instead of unit price 1. So this lagged unit price variable is about 68% important relative to unit price. So this is pretty high on the list, and we can also see that our other 2 lagged variables make an appearance here as well. And these account for the 4% increase in accuracy of our model. So now that we've answered the question about which variables are important and how important they are, we want to look at the actual values of these variables, because we're not sure which unit price would be best for our sales or which weekday would be best. And the way we do that is through a feature called TreeNet Partial Dependency Plots. So when we're back in our TreeNet output window, we'll come down to this button, Create Plots. When I click this button, we see a window that lets us decide which variables we'd like to create plots for. So I'll select one variable dependence plot. This just means that we'll be creating 2D plots of each predictor against its contribution to the target variable sales. And here on the left, we see our variables in the model. I'll click Select All, and this will tell the engine to just include all of these variables while creating plots. That's all I have to do. I'll click Create Plots in the bottom right. After you create your plots, you'll see a plot selection window. You can choose to look at these plots individually, or what I usually do is just click the Show All button. Okay, so the way these plots are created is we have one plot per predictor. So for example, unit price here is plotted on the x-axis with all of the values that appear in the data set. And the y-axis is the contribution to the target variable sales. You can't directly interpret this y-axis as sales. It's the contribution to sales, and this plot has been centered and averaged. So when interpreting these plots, it's best to use the change in x with respect to the change in y. So you want to look at incremental change here. So for example, we can see that the highest point of contribution to the target variable looks like it occurs around 50 cents of unit price of oranges. So this lets you know that these lower prices are better for sales. Once you hit about $1, this contribution kind of plateaus. Doesn't make much of a difference for sales. For state, it looks like RJ state, which is Rio de Janeiro, has the best impact on sales. In the bottom right, we have months. Looks like January is the best month. And maybe July is not so good. Then in the bottom left here, we have one of our lagged variables. These plots can be a little bit trickier to interpret because you are thinking about unit price the day before instead of the day of. So what we can see here is the highest contribution to sales happens around a price of $1.20. Now what this means is that if the unit price the day before was around this value, and the unit price today was about half of that value, you might have a better increase in sales. So this probably means there was a promotion. Yesterday the price was higher, and when people saw that the price dropped today, they bought more oranges, so sales went up. When we scroll down, we can see weekday. Looks like Wednesday is the best day here. We can see our promo variable. Obviously, having a promotion is having a better effect on sales. It's also interesting over here to see that our lagged promo variable is in the opposite direction. So it's actually better for sales to have a promotion today if there wasn't a promotion yesterday. So we use these partial dependency plots to look further into our predictors and see exactly how they're behaving and contributing to sales. In cases where you have continuous predictors such as unit price, we also have the facility to create spline approximations to this plot and export them as transformed variables. I won't show you that today because we still have more to go over, but just keep that in mind. Okay, so the last thing to do here is forecast sales into the future. Before I do that, I wanted to just point out how this TreeNet model compares to a standard regression. So I'll reopen our model setup window, and we actually do have a regression engine. So I'll come to our analysis engine and choose regression. Everything is still selected the same testing method, same lag. I'll just click start. And you can quickly see we're getting about 33% R-squared on the same test sample. So we've about doubled our accuracy by using nonlinear regression methods. Okay, so I'll go back to this TreeNet window. So say that you're happy with this model. You have 69% R-squared. You want to use this model to forecast. The way to do that is through what we call scoring. In the bottom right of the TreeNet output window, we have this button called Score. When you click that, you bring up a Score Data dialog box. There's 3 important steps to scoring data. The first is to open the data file you wish to score. Now, in a typical situation, you'll have a separate data file with records in the future that you want to run through this existing model. Now, because we don't have access to future data in this situation, I'll illustrate the process just by running through the data set that we already have opened. So you can see oranges.csv is already selected here. The second step is to select the model that you wish to score your data with. Now, since I selected the Score button from this TreeNet model, it's automatically populated in here. But you might decide to use a different model if you have another one saved. So you'd open that here. And then finally, you want to decide where to save your score results. So I'll click this checkbox next to Save Scores As. And I'll just save it as oranges_score.csv. I'll click Save. And I'll also check that I want to save all model-related values. And this just makes sure that you have all of the input variables as well in your CSV file that comes after the scoring process is over. So that's all I have to do here. In the bottom right, I'll click Score. So what this is doing is it's running all of our original records back through this TreeNet model and producing sales predictions. Again, in a typical situation, you'd probably be putting in data where you don't know the true value of sales because it's in the future. In this case, since we did have true target variables, values, we are getting prediction statistics here. We see that we have an overly optimistic R-squared of 80% because we're scoring on the same data that we used to build the model. You'll probably see an empty box here if you're using future data. What I want to show you here is I'll open up that file in Excel, and we can see the predictions. So what you get in a scored file, you have your case ID, and then you have this response column. This is your predicted response from the TreeNet model. This is exactly what TreeNet is predicting the sales will be on each of those days. Now we also have a residual column because we do know what the true sales are. And all the columns here to the right are just our original data set. Okay, so now that we've looked at which variables are important, we looked at how they were important through the partial dependency plots, and we also scored the data to produce predictions for the future. I'll go back to the slides now, and I'll just show you some results of scoring that data. So I simply took that scored file, and I just created charts for each of the stores in the file. And I illustrated with different colors. We built the model on this first 80% of the data, and then we tested on the remaining 20%. So we can see here how our model actually performed on that remaining 20% of the data. This right graph here is simply just zoomed in on that little section, so you can see how close it is. So for store 1040, the model actually did a very good job in predicting sales. You can see the orange line follows pretty closely with the black. Now for an example of not so great predictions, store 51 didn't perform as well. You can see there are quite a few jumps in date through September and November where there weren't information on sales, and the engine had a problem predicting specifically this orange spike right here in the middle. So some stores definitely predicted better than others. And this is something you might want to look into further. So I showed you one good store, one bad store. And I also have a slide here for suggestions on further analysis. You could look at performance by store. You could build separate models for each store. You might want to leave out some of the stores with poor predictions, such as store 51. Another thing you could try is play around with unit price and promotion values, see what the optimal combination is there. You might want to put together some hypothetical future data that you can run through your model to see how these would work. It might help you set these values for the future. I mentioned before that you can take lags a step further and include more 2 days before, 3 days before. You might want to look at a week or more, depending on what your data is trying to predict. Finally, you want to use your full data set to build a model when you want to forecast future data, and you want to update as your new information comes in. So in addition to showing you an example of retail, I also included a few case studies to show you the variety of different industries that you can build forecasting models for. This first model, this first case study, is forecasting Alaska's ecosystem in the 22nd century. So Dr. Falk Gutman is a wildlife ecologist, and he is up in Alaska doing research with his team. And they were asked to create a report forecasting how climate change, human activities, natural disasters, etc., might be affecting Alaska's ecosystem over the next 100 years. So this is a pretty big project. It wasn't an easy undertaking. And some of the questions that Falk wanted to answer are included here at the bottom. Will melting ice create new shipping lanes? Will it be easier to exploit natural gas and oil fields or find new ones? So there were several questions that needed to be answered here. And this information was useful for land managers, government agencies in Alaska that needed to make decisions. And they wanted Dr. Falk and his team to provide them with a report to make these decisions. So the way this was done was the team analyzed data on more than 400 species of animals, plants. They analyzed the different diverse landscape biomes. And Dr. Falk actually goes into the field and collects this information himself. And he found that traditional statistical techniques for forecasting weren't working very well in this situation. He had a lot of variables, and he found that random forests worked extremely well. Now, random forest is another one of our data mining techniques. It's also an ensemble of cart trees, just like TreeNet, except it works in a little bit different way. I don't have time to explain the entire algorithm to you today, but just know that random forest is also available for you to try out in our evaluation. So he found that random forest was extremely well suited to handle the data he was working with. It also achieved this with amazing speed. He was able to incorporate all of the predictors he had, and he was able to create this report called the Future of Alaska Report. And it helped out land managers, government agencies, communities, businesses, academics, and nonprofits make decisions on future scenarios. So for those of you who are interested in learning more about this report, for all three case studies I've included today, I also included links to the case studies on one of the last slides. So once you get the slide deck, feel free to check that out. If you have any other questions for us or for Dr. Falk, we'd be happy to answer those for you. The second case study we have for forecasting is atmospheric pollution forecasting. So this is another environmental application. A company called Systems Applications International were involved in a consulting project, and they were interested in a specific pollutant called PM 2.5. Now this is a particulate matter, and it has a diameter less than 2.5 micrograms, which is why it's given the name PM 2.5. It typically comes from wood smoke, vehicle emissions, and vegetation. And the problem is that it can cause respiratory ailments. So this group was looking to predict the concentrations of this specific pollutant so that they could cut back on the problems that it might cause. So they wanted to use CART, which I explained before is classification or regression trees, to classify days by their concentration, group days with similar concentrations, determine key relationships and parameters, so develop forecasting algorithms. So they wanted to predict the daily maximum PM 2.5 in a specific area using variables such as temperature, humidity, wind speed, wind direction, rainfall, and they also use lag variables here. You can see it says PM 2.5 values from 2 days prior were used to predict PM 2.5 values on that specific day. Again, I'll just mention that I'm giving a brief overview of these case studies. The real case studies have a lot more information, so if this is something that's of interest to you, please go ahead and follow the links at the end of the presentation to get more details on the actual analysis done. I've included here the CART tree from the case study. Now, instead of a regression problem that we looked at today for sales, we're looking at a classification problem here. The company grouped 4 different classes of PM 2.5 concentration. You can see these at the bottom of the tree, classes 1 through 4. Now to explain this tree a little further, you start at the top of the tree with 365 records. So this is 1 concentration for every day of the year. The first data partition happened at this split, where RH was less than or equal to 65%, and RH is relative humidity. So based on the relative humidity of that given day, the records either went to the left or to the right. Now the 200 days of the year that went to the left were then split based on the wind speed of that day, and subsequently placed in either class 3 or class 1. And below the classes, you can see the different concentrations of the particulate matter. On the right, the 165 days were split based on the wind direction. So this is a pretty simple example of a cart tree. This is not a cart tree straight from our software. This is a cart tree used in the study of this company. And it resulted in 80 to 90% of days of the year being correctly classified. So this is a high classification accuracy. In addition to a high accuracy, they were able to derive relative importance of the input variables. So this is also what we saw in our oranges example of finding out which variables were important. And most importantly, they were able to develop a forecasting tool that uses this cart tree to decide which days in the future would have higher concentrations so that maybe they could make some changes in that specific area. The last case study is a bit of a different industry. We're looking at forecasting economic recessions. This case study comes from the Federal Reserve Bank of St. Louis. They had information on 6 recessions that have happened between January 1960 and September 1999. And if policymakers can anticipate a recession, they can take some corrective actions ahead of time. And typically, many economic studies use Probit models to estimate probability of recession. Now, the problem with the Probit specification is that causalities are assumed fixed over time. And this is a problem because we know that in the economy, things are constantly changing. And so the analyst here wanted to find something that was a little more flexible. Additionally, the analyst has to choose variables included in a Probit model and determine their level of interaction. So this particular analyst in this problem decided on using MARS to compare to the Probit model. And MARS stands for Multivariate Adaptive Regression Splines. This is another nonlinear data mining technique available in our software. A lot of the same advantages that CART and TreeNet have. There's automatic predictor selection, interaction detection, and it incorporates nonlinearities. So in this specific problem, there were a few questions that needed to be answered. How well does MARS fit the historical data? So this is in-sample data. And that question was answered. In the graph to the right on the top, you can see the in-sample forecast of recession for 3 months and for a 9-month period. And the conclusion that was that MARS fit historical data much better than the Probit model. The second question was, can information on financial variables help predict recession in the future? So this is out of sample data, and those are the bottom 2 graphs to the right. The conclusion there was that MARS didn't always predict better than the Probit model, but it did hold some promising results that could possibly be tweaked and used for quarterly data or monthly data instead. They also wanted to know how likely recession was within the next few months. So MARS did a great job of fitting historical data, and it showed promising results for the future data. So just another example of how data mining techniques are more flexible and are popular in the economic industry. For those of you in other industries, I have listed here some other applications: environmental, such as predicting the weather or earthquakes. Forecasting can also be used in the medical field, such as looking at the spread of disease. You might look at the onset of diabetes. Here I have an example of predicting Parkinson's disease progression. And these are all live links that you'll be able to click once you get the slide deck. You can also forecast the household power consumption. Might be useful for energy companies. And then finally, we have retail, forecasting demand or forecasting sales, like we looked at today. Just a quick summary of what we learned today. We were able to forecast the sales of oranges by using information about the store, as well as price and promotions. We saw the advantage of adding lagged variables for price, promotion, and sales. It increased our forecast accuracy by 4%. And that increase in forecast accuracy was just on a first run. There were always more parameters, more advanced controls in TreeNet that we can change and possibly squeeze a bit more accuracy out. Today was just a quick illustration on how quick and easy it is to run a TreeNet model. We also saw via the case studies that other data mining methods such as CART, MARS, and random forests are also powerful forecasting techniques that tend to overcome the issues of conventional statistical modeling. And then finally, we know that forecasting can be risky, but when done right, it can provide great insight into your data. So here on the references, I have the 3 case studies. These are the links you can follow if you want to find out more about the Alaskan ecosystem, the forecasting recessions, and the atmospheric pollution forecasting. So I believe we had some questions come in. Any questions that I don't get to answer today, I'll answer via email directly to the address you provided when you registered. And then if you have any questions after the webinar, they can be sent to support@salford-systems.com. Again, I'll just reiterate that you'll be getting a follow-up email either today or tomorrow that has the recording of this webinar, a 30-day free evaluation of the software, the Oranges dataset, a tutorial on the demo that I gave, and the slide deck. So thank you for joining us. I'll take a look at a few of the questions, and the ones I don't get to, I'll address later today. This is our last webinar of this year, so look for more webinars in 2016, and if you have any suggestions on topics for webinars that you'd like to see, please feel free to send those to us. Okay, so one of the questions we have is, what exactly is the one telling SPM in the lag screen? This means that we're just lagging that variable by 1 record. So we're just looking at the record previous to that. So if we put a 2 in there as well, you would be looking at the record lagged 2 back from that. So as I mentioned before, if you want to look a week ahead, you'll put in 7 if your sales data is daily. Another question is, I see the non-lagged sales variable is not listed. This is because we're using the non-lagged sales variable as our target variable. This is what we're trying to predict, so it won't show up in the list as a predictor. But we are using the lagged sales variable as a predictor. Another question is, does the outcome need to be binary always? No. In this case, our outcome was sales, and this is a continuous target. So you can use all of these techniques for both classification or a binary target, as you mentioned, or for regression, as we looked at today. Another question is, do you have a feature that could export all of the GUI methods into code, like a macro? So we do have a feature in the software called Translate. And the Translate feature, I believe, is not available in the evaluation you'll download today. But if that's something that you'd like to explore, go ahead and send us an email and we can turn that on for you. And you can translate any of the models that you create into SAS, C, Java, or PML. Another question is how to deal with character variables if they are not a number. So character variables are automatically recognized by the software, and when you import them, they'll be appended with a $sign. And they will be treated as character. And so if you think about how I explained with a cart tree when you're partitioning your data and you're sending certain values to the left and certain values to the right, the same thing will happen with a character variable. This is automatically handled by the software, and certain values of your character variable will just be sent to the left of the tree, and certain values will go to the right. So it's handled for you. You don't have to change anything about that. Another question is how to determine which independent variables to include in the model. The great thing about these techniques is that they are automatic predictor selectors. So we typically include all the variables that could possibly be in the model, and Cart and TreeNet decide for you. They go through a system of ranking these variables by importance based on their contribution to the target variable. And so they will be selected. As we saw earlier, climate was automatically left out of the model because it was deemed not important. So you don't have to determine manually which independent variables you want to use. It will be done for you. Another question is, why did you add month as a group ID? So the reason we had to add month as a group ID is because we had discontinuity in our dates. So for example, in January, we only had a week available of sales data, and then it jumped to February. We also had to denote this as a block so that the lags would start over when the month changed. Otherwise, February 1st would try to use a lagged variable from January 7th, and this wouldn't make a lot of sense in the analysis. So a few of these other questions are a little more technical, looking for detailed documentation on how R-squared is calculated. So we're about at the hour, so any questions that are left over, I will address them by email later today. I'll send it directly to you. And if you have any more questions, please submit them to support@salford-systems.com. Thank you again for joining us, and look for more webinars in 2016. Thank you.